So for some of you who are looking for something to do, for fun, you might ask about what this relationship here is when you figure it out. Because there you're going to be putting 2x's and 3x's down there, and you're going to be combining them in the Rice expression. Some of you might also find this kind of interesting. If x squared goes here, and 4x cubed goes here, and 27x to the fourth goes there, I bet that's a pattern mathematically, and I bet it's actually kind of famous. So that's kind of a nice thing for you to be thinking about. For those of you thinking about pushing ahead in terms of understanding this, it's nice to work these particular problems. For the rest of us, here's a nice simple pattern I'd like you to appreciate. That the number in the exponent here is equal to the number of species going in solution. 2 species go in solution, I square. 3 species go in solution, I cubed. 4 species go in solution, fourth. 5 species go into solution, fifth power. So I now have a rule of thumb I'm about to tell you for any time you want to do molar solubility calculations. And it is this. Look at the kind of salt. I don't care what it is. Here's a salt right here. Here's Al2O3. The second I look at that salt, I count up the number of species going in solution, 5. I know that whatever the KSP is for this, if it's about 10 to the minus 100, take the fifth root. The molar solubility is 10 to the minus 20. If I'm tossing something like calcium chloride into solution, and the KSP is around 10 to the minus 12, that's 3 ions going in solution. The molar solubility is around 10 to the minus 4. This is wonderful. This is why it is ultimately, I love doing solubility product problems to start, is because it gives us the opportunity to develop this really simple rule of thumb where we count up the number of charged particles going into solution per salt, and that is the root that we take when we look at the exponent for the KSP. Did I make that up? No, I mean, it's obvious. But it's the kind of thing you want to take away from experiences where you're doing mathematical development for different kinds of chemical systems, because it gives you simple rules of thumb for doing problems later on. Does it always work? No. There are going to be cases where that exponent that you're forgetting about, that factor that you're forgetting about, that 27 or so, really does matter if the KSPs turn out to be much, much smaller kinds of exponents. But as a general rule, when working with sparingly soluble salts, you can get away with this little trick that I'm showing you. It's much, much faster, and it keeps you from having to even look at a Rice expression. Notice that as I work the problems on this page, I didn't draw my little array at all. I just counted up a number of particles and did a square root, a cubed root, a fourth root, a fifth root, and I had my answer. Summarizing. As we started this problem right here, this experience right here, this was our first quantitative foray into looking at water chemistry specifically of salts. And what we learned was that instead of talking solubility rules, instead of talking about principles associated with the physical equilibria, things like the fact that highly charged compounds tend to not dissociate and like dissolves like, we have moved full steam ahead, just like we did back with thermodynamics, full steam ahead into a mathematical treatment of what's going on. Now, I'm not concerned with saying that's kind of soluble, or that's kind of salty, or that's really salty, or that's really didn't dissolve, and I've replaced it with numbers like, that's 10 to the minus 5 molar, that's 10 to the minus 2 molar, that's 10 to the 5. Those numbers give me real live concentrations. Granted, usually they're approximations, but they're pretty good quantitative estimates of what is going on, and they give us our first exposure to just how powerful chemical equilibria is in problem solving.